Okay, so that's the first case. The second case is now so in this case, we assume gamma is defined by gamma 2, the minimum of the three quantities. And the updating in that case is similar. XBI is the current value minus YIK times gamma for I in. Okay, we already investigated the condition when gamma is less than UK minus LK, so I'm looking at the case when gamma is equal to UK LK. In this case, of course, the updating is true for each of the basic variables. So all of them are still basic. They don't change their status. The non-basic variables, xj, they are at the lower bound for j in R1 except k. And xj are at the upper bound for j in R2 except k. And finally, so these are still non-basic. And xk is now at the upper bound because it will be Lk plus gamma, which gives you Uk. Okay? Okay? That's how much it is. All right, so this is also still non-basic, these as well as that one. How does that reflect into the tableaus? The current tableau for basis B has the following information. You have identity for xb. You have B inverse n1 here, B inverse n2 here. You've got B cap on the right-hand side column. You put B cap here, okay? Don't think of it as the old case. It's not B inverse times the entire thing. B cap is different from B inverse B, okay? B cap is B cap. And also you've got Z cap here, which is somewhat different from the old situation, okay? And here you've got 0, the reduced cost for the first type of variables, and reduced cost for the second type of non-basic variables. That's the current tableau relative to basis B. Okay? And in the new tableau, we just saw how to update the right-hand side column. So the right-hand side column will be Z cap new, whatever the new value is. I did not tell you how it is, but we'll work it out. It will be B cap new now. The B cap new is as I defined in the updating. Okay, the updating I gave you in the former case and in this particular case, they were like this. All right. The other parts, compute the rest of the tableau by pivoting on the pivot element, YRK. If gamma is defined by either gamma 1 or gamma 2. Okay? So, what about if gamma is defined by UK minus LK? In that case, you don't need to do anything because the new basis is still the old basis, okay? In that case, no changes in basis occurs, which means everything else is the same old stuff as in the old Tableau, okay? Of course, the reduced costs are also computed via pivoting, if you need to pivot, okay? So, it's only this part that changes. And I already told you how to update that part. Except Z-new, I did not tell you. How do we update Z-new? Well, it's simple. It's going to be the old value, which is Z cap, which is already computed. And how do we change that? Well, it's RK times XK minus, well, delta, RK gamma, yeah. RK times gamma if K is in R1. What about in the other case? In the other case, it will be Z cap plus RK gamma. If K comes from R2. In that case, of course, RK is negative, so gamma is positive, so you're still going down. Okay? How did I know this? Well, we already computed Z as dependent on the new xn1, xn2. Only one component of those non-basic variables have changed, and that change will simply amount to this change. Okay? So, if you don't believe me, you can go back and actually just make sure you understand why this is the situation. This is the case. All right, I'm not going to give an example on this because it takes too much to work out an example. This was the situation when some variable, we decided to increase it, right? Xk was a variable that is at the lower bound is now being increased. Now there's another case when it's at the upper bound and it's being decreased. So this is the second situation. Xk is non-basic at its upper bound. You are going to decrease it. Which makes me realize that, let's just go back here for a moment, because I just realized that this case is not really applicable here. So let's just cross that. In the first case, we assumed K comes from R1, so this is the only case that's applicable. Okay? Erase this. The second case will be applicable now. So in this case, z cap nu will be the old one plus rk times gamma, where gamma is the new value of the variable. How do you compute gamma? Well, again, you look at the minimum of gamma 1, gamma 2, and gamma, UK minus LK. Where gamma 1 is still defined by the minimum of the ratios bi cap minus lbi divided by yik for I coming from okay, let me change gamma 1 to let's put a minus here, okay? Let's put it that way, okay? Gamma 2 is the minimum of u bi minus bi cap divided by yik, I coming from plus. Just a second. Yes, what is it? This is correct. This is plus in this case. Is that what you're asking? No, this is correct. At least that's what my notes says. It should be this way. I'm sure we can work it out. I'm just too lazy to do it. But all you have to do is you're looking at the basic vector, which is the current value times yk times delta. Delta is the amount you go down from the current value, upper bound, downwards. Okay? Now, is this a minus or a plus in this case? I think it's a plus here. For that reason, we've got that. Let me just see. It's at the upper bound. Yeah, it's a plus here. Okay? And this is the situation. So let's just make sure. This is a plus here. That's where it comes from. And that's, in this case, you want bi cap plus yik delta to be greater than or equal to lower bound for I in, I plus. And you want that to be less than or equal to the upper bound for I in. Just a second. Did I do it right? So, when yik itself is minus, this is going down. Yes, this is going down, so it may hit the upper bound. That's why you've got that. And for the other ones, coming from the plus set, you have to make sure that they don't go up too much. Okay? And of course, this gives you two kinds of ratios. The first one gives you gamma, if you look at the minimum of these ratios. The second one gives you gamma 2. Okay? So it looks correct. Okay? So the updating is almost the same, except for the case of gamma defined by UK minus LK. If this is the situation, then of course xk remains non-basic, but switches from the upper bound to the lower bound. So that's the only thing you need to pay attention to. Okay? So there's only one issue left, how to find a starting or initial basic feasible solution to lower upper bounded problems. Now, if you just try your luck and take some variables at the lower bound, some variables at the upper bounds, and allow the remaining ones, m of them, to be basic, you may or may not obtain a basic feasible solution. Okay, that's obvious. So you need to know how to initiate the two-phase method for this problem, phase one. So you want to begin with artificial variables. You insert artificial variables as initial basic variables. And use phase one. So you want to use the phase one problem, minimize the sum of the artificial variables, subject to the appropriate constraints with artificial variables supplying you the initial basic feasible solution. So when you add the artificial variables, the problem will look like the following. Let's just give a name to that. Let me just see, what did I give? That's XA. Let's call it x sub a equals b. So these are artificial. And you want to minimize the sum of the artificial variables. Still, you can't take x to be 0. If you were able to do that, xa would be equal to b. And if b is non-negative, then that's the only requirement on the artificial variables, that you want them to be. So we want xa, whatever values they will assume, we want to make sure that they are non-negative. Okay? There's no upper bound for that. Now, we cannot take x equal to 0 because x must be at the bounds, between the bounds. Okay? So in this case, partition A in the form say n1, n2 in some way, meaning almost in an arbitrary way, okay? Just partition in some way. Whichever ones you want to put at the lower bound, put them at the front. The other ones are will be at the upper bounds, okay? And set xn1 equal to the lower bounds, xn2 equal to the upper bounds, okay? Then, of course, the system ax equals b, well, ax plus xa equals b gives, what does it give? This part is partitioned now. It will give you n1 ln1 plus n2 un2 plus xa equals b. That's what it will give you, okay? So xa is actually equal to b minus n1 ln1 minus n2 un2. If it so happens that this assigned value to xa is greater than or equal to 0, begin with this solution. Okay? So xa will be the basic part, all the rest will be non-basic, and everything is feasible now. Okay? If not, that means at least one component here, that's your b cap now, some component is negative in that case. Then what do you do? Then what you do is multiply the equations as necessary by -1 so that the negative right sides become positive. I'm not talking about the equations with artificial variables in, but I'm talking about the original set of equations. Okay? So then multiply the equations ax equals b by -1 as necessary, i.e. corresponding to the negative components. Then insert the artificial variables. So, let me have your attention. You tried your luck. You picked certain variables at the lower bound, certain variables at the upper bound. And then you solved for the artificial variables, or you just computed this here, b cap. If b cap happened to be non-negative, then you just begin with that. If, on the other hand, b cap happened to violate non-negativity in at least one component, then you said to yourself, well, then whatever negative components I have in b cap, those constraints in the original problem, I'm going to multiply them by -1, so they will be switched in sign. And then I'm still going to use the same lower bounds and upper bounds for my initial choice of variables. But then after multiplication by -1, when I insert the artificial variables afterwards, things will be okay. Okay? So you're converting this to a new system, say A tilde x equals B tilde, due to multiplication by -1 for some rows. And after that, you're inserting your artificial variables to the system in this form. Okay? So that XA in this case, or the B cap relative to the new system, will be okay. Okay? Now, no numerical example for you, unfortunately, because it takes too much time to work it out, and it's hard to work it out on the board. But your book has a good number of examples, so work through them, and you will get the idea. And in fact, some of the problems I asked you should be also numerical. Okay? So if you want to spend time on numerical examples, you have some material to work on. Okay? That's it for bounded variables. I hope everything is crystal clear now. So, I'm going to switch to a new topic, duality, which is an important topic. I'm sure many of you are familiar with duality from before. So let me just give you a brief introduction, at least today, and some motivation for the dual. The dual problem, well, for any linear program, there's another linear program which uses the same data but in a somewhat different way. So the derived problem with the same data is called the dual problem. To motivate the dual, let's just look at a problem of the following sort. Suppose, say, we're minimizing Cx subject to Ax greater than or equal to b, x greater than or equal to 0. So this is the canonical form minimization problem. Okay? Well, let's forget this. Let me just take it this way, where a x greater than or equal to b possibly includes non-negativity as well. Okay? So I'm looking at a very general form, where every inequality is expressed in this way, and you're minimized. Okay? Now, in the general formulation, if you had equalities, you can always express an equality constraint by a pair of inequalities, one going one way, the other one going the other way, and then multiply by -1 as necessary so that everything becomes of this form. Okay? So this is the situation. Let's take. So this is not the canonical form. So what I'm going to do is, suppose I'm going to choose a non-negative vector w so that w, this is a row vector. Suppose I choose a non-negative row vector w so that W times A is equal to C. So I'm trying to express the cost vector in terms of the rows of the A matrix by multiplying each row of the A matrix by appropriate non-negative numbers. Okay? So that when you add, I want to make sure everybody understands this. You've got your A matrix here, which has many rows here. Okay? You take W1, a non-negative multiplier, multiply it with the first row. You multiply the second row with W2, so on and so forth. These are all, and suppose you've got, say, K rows. So you simply multiply these rows by appropriate non-negative multipliers, add them up, you get a single row vector. And that row vector is actually the objective function's cost vector. Okay? Then we may use, in place of C, we may use WA in the objective function. So Cx becomes WA times X, because I expressed my C in terms of the rows of A. Since W is non-negative in each component, I can actually multiply the constraints themselves by Wi, the ith constraint by Wi, multiplying the ith constraint by Wi on both sides gives the following. You're multiplying Wi times the ith row of the constraint. And so you get this on the left. On the right side, you're multiplying the right side by Wi. Since Wi is non-negative, the sense of the inequality does not change. Otherwise, it would change. Okay? So that's why we required non-negativity. Adding up all constraints gives, well, you're simply adding all the constraints after multiplication. So on the left side, of course, we've got Wi times Ai, x, I going from 1 to k. We've got k constraints. On the right side, we have Wi Bi, I going from 1 to k again. So inequalities are preserved, and so you've got this. But what is this? This is actually the weight or the multiplier Wi times the ith row. So you just do this one at a time and add them up. So what you have here is nothing but Wa. That's precisely that. Okay? So over here, you've got the vector, row vector W times the column vector B. So this is simply telling you that your WA, which is your new cost vector, times X is greater than or equal to WB. That's what it is telling you. And this is, in fact, your Cx, or that's, in fact, your C. So this entire thing tells you that as long as your W are non-negative, you've got Cx greater than or equal to WB. And we arrived at this conclusion by only assuming that W is non-negative and it gives you C. Okay? So two conditions. W is non-negative, and it gives you C. In which case, Cx will be greater than or equal to Wb, as long as, of course, x is such that the inequalities are not reversed, okay? So, let me have your attention here. This was only for one W. And I just realized that when I do this, because of the way we construct, we just find that Cx for feasible x, as long as you retain your inequalities, is bounded below by Wb. Okay? Because this part is equal to C. So, I'm trying to minimize Cx, and if this works for one W, then it will work for every such W, as long as W is non-negative and gives you C. So, the maximum bound I get will still be valid bound for Cx here, okay? So, what am I trying to do? I'm trying to push this number upwards to still get the, most meaningful bound for the objective value of the minimization. For that reason, you're trying to maximize Wb by making sure that Wa equals C and W is non-negative. That's your dual for the problem here. Okay? If you call this primal, that's the dual problem associated with that. And there's some good reason for doing that. I don't know if that really made sense to you or not. Okay? To me, that really makes sense, but of course, I live with these things for some time, so, they actually, after a while, they become part of you, But for a newcoming person, it may look a little bit strange. Anyway, I don't know how it was discovered in the first place. Well, the original inventor is Danzig himself. Also, in the context of economics, the well-known mathematician von Neumann also actually came across to the idea of duality in a different context in linear programming. Whether or not this was the motivation, I don't know. But this is the motivation I got actually one day. I was talking to a student. This student was a kind of a person who doesn't give up on anything. He must get the solution. That's the kind of person. And there was a numerical linear programming example in 2 variables or whatever, just a few constraints. And this is the initial first, 1 or 2 weeks of linear programming course in undergraduate. He didn't know how to solve the problem, but I happened to ask for a solution, just intuitively. And then he thought about the problem. He had all these inequalities. So he said to himself, first I didn't know, but that's later on when I talked to him. Apparently he was trying to figure out, since the inequalities involved all these constants on the right side, he chose some wi's actually numerically, so that Wa was actually equal to C. He actually intentionally did that. He wanted to make the objective function C vector look like, or he wanted to obtain that in terms of the rows of A matrix. So that when he applied the same multipliers to the right side, he actually had a bound. And he happened to pick the very best wi's so that he obtained the best bound, the best bound, if you maximize. And then he was able to solve that. That was very interesting. Well, he wasn't able to really solve it. He was trying to explain it to me. I didn't quite understand what he was trying to do. But then, after maybe, a few minutes of arguing back and forth, he was feeling kind of bad because I didn't quite absorb the details of what he was doing. But then, all of a sudden, it sank on me. he was actually doing the dual operation. You know, he was actually working with the dual problem. He didn't know anything about it. But it's intuitive. At least for that person, it was intuitive. So after that, I really liked it. And I sort of gave you the general idea based on that particular intuition, okay, at least intuition to some people, okay. So this is how you get your dual problem, and of course, does that make sense to all of you? Okay, all right. So that was just the motivation. So let me give you the dual problem in canonical form. The canonical form minimization problem is just the minimization of Cx subject to Ax greater than or equal to B, x greater than or equal to 0. That's the canonical form minimization problem. So you may simply apply the foregoing idea, the motivation idea, to the problem with A and identity forming the left-hand side matrix, okay? And if you do that, the dual problem, so if you call this the primal, well, let's just call it P, the dual is a maximization problem as here. It's the row vector W times the column vector B, so the objective function is precisely the same, subject to W times A is less than or equal to C with W non-negative. That's what you get. You would be able to get this from the foregoing idea. How? Or why? Because in that case, if you apply the foregoing idea, your original problem has AI on the left, and you've got the B and 0 vector on the right. Okay, that's what you've got. So that when we talk about W, we have W's associated first with the rows of A, and then maybe, say, V associated with the rows of identity, okay? So that if you apply the idea, you have maximization of W and V times this vector. I'm just applying it to that idea, subject to WA equals C. What is WA? In this case, it will be W and V multiplying A and I equals C, with W and V being non-negative as a vector. Okay? And this, of course, gives you the maximization of WB plus V times 0, which is 0, subject to WA plus identity times V, so that's going to be V equals C with W and V being non-negative. And of course, V in this case is just a vector of slack variables, if you want to think of it that way, because, you know, coefficients at the top are 0, and so they are just slacks. You can just think of them as slacks. So this is simply equivalent to the problem of maximizing WB with WA less than or equal to C, if you just get rid of the slacks, and W being greater than or equal to 0. So this actually can be obtained from this original idea. Okay? That's the canonical form, primal dual pair for this. And canonical form maximization is just a maximization problem. Cx subject to ax less than or equal to b with x greater than or equal to 0. I must have given you these at the beginning of the course. Did I give them? Okay, yeah. I remember all of a sudden. Okay, so that's the canonical form maximization. This is the canonical form minimization. And the dual of this is going to be a minimization problem of the form WB being minimized subject to WA greater than or equal C with W non-negative. Okay? Again, you can derive this from the initial motivating idea. Primal dual. Okay, maybe we should stop here. Next time on Wednesday, we're going to talk about some duality theorems and so forth. Okay?